It is 3:14 a.m. on a Tuesday. An agentic code review pipeline, one that had performed flawlessly in every executive demo, has just entered a retry loop. The trigger is entirely mundane. The agent encountered a transient error while trying to ping a flaky third-party static analysis API. In a standard system, this causes a minor blip, but this pipeline operates without structural constraints. There is no circuit breaker, there is no cost ceiling, there is no timeout policy explicitly instructing the agent to stop trying. Over the next 33 minutes, the agent frantically pulls the unresponsive API. By the time an engineer wakes up and kills the process at 3:47 a.m., the agent has burned $412 in API calls. The pull request it was supposed to review remains untouched. The downstream deployment pipeline completely stalls. The morning stand-up turns into an incident retro, all for exactly zero useful output. The uncomfortable truth of this incident is that the agent is not malfunctioning. Given a task and no boundaries, it is doing exactly what a foundation model does by default, trying repeatedly until forced to stop. During the postmortem, the engineering team looks for the flaw. The model itself performed perfectly. The prompt was highly optimized and detailed. The failure exists because the runtime infrastructure layer does not exist. The team deployed a naked model directly into production. Renting an API connection to a foundation model from OpenAI or Anthropic is the architectural equivalent of buying a raw CPU off an assembly line. A CPU on its own cannot manage memory, schedule tasks, or interact safely with a network. Without an operating system to constrain and direct its mathematical capabilities, a bare CPU is simply a piece of silicon that gets hot. The discipline of building that necessary operating system around an AI model is called harness engineering. The harness provides the runtime infrastructure that constrains, verifies, and observes the agent. The distance between a successful demo and a reliable deployment comes down to this missing layer. Without a harness, a team is essentially running a raw processor and expecting it to function as a managed, secure enterprise system. How human engineering teams work with AI code agents follows a distinct three-phase maturity arc. Phase 1 is vibe coding. This is an intuition-driven workflow where a developer opens a chat window, describes a goal, runs the generated code, and iterates. There is no specification, no architectural plan, and no verification beyond asking if the output feels right. For rapid prototyping, this works, but when these agents are deployed into enterprise production, the output is untraceable. When a vibe-coded agent fails, teams cannot debug the resulting hallucinated architecture because they cannot answer the basic audit question: what was this agent actually supposed to do? This leads to Phase 2, Specification-Driven Development. This approach strictly requires upfront planning. Requirements, design, and acceptance criteria are written out before the agent is allowed to generate a single line of code. Teams often resist this discipline because writing specifications takes time, but the initial velocity gained by skipping a formal design is immediately lost when engineers have to decipher an erratic, undocumented agent behavior at 3 in the morning. AWS Kuro's spec mode enforces a rigid 3-document workflow. The agent generates requirements, design, and implementation task documents. Crucially, a human approval gate sits between planning and execution. The agent cannot write code until a human approves the specification. To make these specifications explicit, engineers use structured templates like ears notation, the easy approach to requirements syntax. Instead of a vague conversational prompt like, make sure it handles errors, ears dictates a strict trigger and response syntax. For example, when an API returns a 503 error, the system shall execute an exponential backoff. Because this notation is unambiguous, an agent can generate acceptance criteria in the EARS format. A verification layer can then evaluate whether the implementation satisfies those criteria, completely eliminating the need for human interpretation of the results. By enforcing this structure, vague engineering ideas are converted into formal, mathematically verifiable rules. This establishes the exact kind of rigorous audit trail that compliance regulators demand in production environments. Specifications tell the agent what to build. Phase 3, harness engineering, dictates how the runtime enforces the agent's behavior while it works. Architect Martin Fowler argues a safe system relies on hard walls. The LLM's judgment operates inside, but never overrides them. First, context management restricts visible files. Second, tool access control limits external invocations. Third, Deterministic tests must pass before proceeding. If you grant an agent unrestricted file modification and tool access to maximize its flexibility, you have built a rogue service account with admin privileges. This diagram shows a recovery policy, a hard ceiling on task spend and attempt limits, the circuit breakers that prevent 3 AM loops. Next, observability telemetry tracks every decision and token cost. This tracing extends outward, preventing multi-layered retry cascades. Finally, safety boundaries define what the agent is absolutely prohibited from doing, establishing rigid guardrails to handle adversarial inputs or emergent behaviors that the initial specification could never anticipate. Without this level of deep observability and strict recovery logic, you cannot debug or optimize the workflow. You have a system you can deploy, but you do not have a system you can operate. Building this system requires a specific implementation sequence. Before you write a single prompt, you must define your read scopes, set the timeouts, and establish your cost ceilings. This document is the agent's operating agreement. It acts as non-negotiable infrastructure policy, governing how the entire system behaves. As shown here, these specifications must be treated as versioned artifacts. When an agent receives a task, the exact version of the specification file it is working from is pinned and locked into the commit history. Failing to lock the version causes a severe failure mode called spec drift. The agent confidently and flawlessly implements a feature at scale, completely unaware that the requirement it is satisfying was deprecated 2 commits ago. The specification is a living contract. Pinning its exact version to specific agent executions is the only mechanism that guarantees the final codebase matches the current architectural reality. For organizations in mortgage finance, healthcare, and banking, the ability to account for every agent decision is a non-negotiable legal mandate. When an auditor demands to know an AI's behavior, the specification document explicitly proves what the agent was supposed to do. The observability trace objectively proves what it actually did. The broader industry remains focused on gaining access to the newest foundation models, but next quarter's model will naturally outperform today's. Teams relying entirely on raw intelligence are betting their competitive advantage on a rapidly depreciating commoditized asset. The durable value resides in the proprietary harness infrastructure. The verification gates, the context controls, and the observability streams form the operational layer that forces a chaotic model to produce reliable work. The foundation model is a rented engine. Harness engineering is the operational moat that dictates which companies will actually survive deploying autonomous agents in production.